I wanted to do a little bit of a review for hypothesis testing with variances, as well as remind you a little bit more about the type 1 error and type 2 errors that you could come up with in a hypothesis testing. So let's look at problem 7.4-7. This one says that you have a random sample of size 19 taken from a normal distribution, and part A first asks you to find a critical region of size alpha equal to 0.05 for testing the null hypothesis that the variance is 30 against the alternative hypothesis that the variance is 80. So in this case, notice that the alternative hypothesis being equal to 80 versus saying being greater than 30 or less than 30 has very little to do with actually finding the critical region, because remember again, the idea of finding the critical region is trying to find a region where the probability is that you reject the null hypothesis when you're not supposed to. That needs to be small. That's the alpha value. So remember, the alpha again is the probability that you make a type 1 error. So that's rejecting the null when you shouldn't. So assuming that the null hypothesis is true is how you get to the critical region. So again, the alternative hypothesis here being 80 isn't any different than what we would do if it were greater than 30 or less than 30 or not equal to 30, really. We're doing the same kind of idea. Now, we do know that if there's only two possibilities of 30 and 80 is certainly above 30, we are to look for a critical region that's above the, to the right of the right tail test here. Sorry, apologize for that. We're looking for a right tail test here because, again, the alternative is greater than the the null hypothesis value here. So that's why we're looking at a right tail here. This alpha is equal to 0.05. So again, we want to find a critical region associated with this hypothesis test and this sample size. Now we'll remember that if we have it calculate the sample variance, multiply it by n-1, and divide by the population variance, that gives us a chi-squared distribution. So that's why we're using the chi-squared here to figure out the critical region. In this case, it's a random sample of size 19, so our degrees of freedom is going to be 18. We've got a right tail test, so our alpha is 0.05 is on the right-hand side. So we want to find that chi-squared, so 0.05 of 18. You can use the table in the back of the book, or use Excel using the equals chi-square inverse function. Just to remind you of what that looks like. If I go over to Excel real quick. So if we say equals chi-square, so we see the chi-squared one, we want the inverse dot right tail, because we're looking off to the right again. The probability that we want associated with that right tail is 0.05, and there are 18 degrees of freedom. So that gives us that critical chi-squared value of the 28.87-ish. All right. So going back over to the right up here. So that's how we found this value. Now associating it back to the sample again requires with the sample variance. So if I get this expression again with the sample variance, remember we said that n-1 times the sample variance divided by the population variance, that gives us the chi-squared value. So we'll reject H0 if this test statistic is greater than 28.87, or if you want to do a little bit of algebra, you'll reject if the S squared is greater than the 48.1 and 2. Now, again, like I mentioned in class before break, usually I would leave it as this statement, because remember when we go back to Z's and T's, we actually calculate a test statistic. And with the video that I posted with the F distribution, notice again, you do an actual quotient of two things. You're calculating a test statistic. So I like to leave it in this form because this form, again, is consistent with those other forms. We have a critical value based on that underlying standard distribution, if you will, either using a normal, a T, a chi-squared, or an F. Okay, so we use that underlying distribution. That's where that critical value comes from. And we calculate a test statistic, which transforms the distribution that we have into that standard distribution that we're comparing it against. Okay, but you can always do it this way too. There's nothing wrong with it. I just like to do it in the other way, like I said, the first way, just to be consistent with what we've been doing all along. All right, so this is our critical region that we would be interested in. So if we were going to reject whatever the sample was, we would calculate the sample variance, multiply it by what? Is that 3/5 in this case? If I would to simplify that and check to see if it's bigger than or less than the 28.87. All right. So let's look at part B now, where it asks you to approximate the probability of the type 2 error, to approximate that beta value for the critical region. All right, so remember beta, again, is calculating the type 2 error is rejecting when you, not rejecting when you're supposed to. So the probability that, or excuse me, we want the probability that the null hypothesis is false, the probability the alternative hypothesis is true, but you didn't reject it. So looking at that, to figure out what beta is, we reject if the s squared is greater than the 48.12. So really what we want to find is the probability that the s squared is less than the 48.12, given that we're supposed to reject, given that the variance really is 80. All right, this is not in our standard chi-squared distribution form, right? Because we have to transform the sample variance. Now remember again, we're assuming that the chi-squared is that the variance is 80 here. So to transform this into the chi-squared distribution that we want to calculate the probability associated with, I needed to multiply by 18, n minus 1 again, but I need to divide it by 80 in this case, because remember, to calculate the probability of doing a type 2 error, the alternative is true. The alternative says that sigma squared is 80, so I'm going to divide both sides by 80 here to transform it. So just to save me some writing, I'm going to call this the letter m here. So this 18 times 48.12 divided by 80. I'm going to call that m. I want to figure out what this probability is. So let's go over to Excel again. All right. So this 28.8693. Sorry about the zoom. This being a pain there. This 28.8693 was the chi-squared. So if we want to multiply that by 30, I want to multiply that value by 30 and divide it by 18. That gives us that s squared value that we said we had to be greater than to define the critical region. I want to move this backward, if you will, for the chi-squared probability. So I can find the chi-squared probability here. So use chi-squared.dist. It's this value, but remember I want to multiply that by 18 and divide it by 80, transforming it to the chi-squared distribution, assuming the variance is 80. And then I want it, I want it less than this. So I want to use the cumulative as true. The degrees of freedom, again, was 18. So then the cumulative is true. So again here, s squared is the 48.12 that we're trying to compare to. We're transforming it to a chi-squared distribution. So that's why we're multiplying it by the degrees of freedom and dividing it by the variance. There's 18 degrees of freedom, and it's true here. And we hit enter. We get about 0.098. So going back over to my write-up over here, using the chi-squared distribution, we figure out that beta really is the point. About 0.098.